Hello everybody, welcome to Blue Marble Science. I don't usually comment on visual observations, especially not the ones over water, because typically they're done at such short distances or during such horrific atmospheric conditions that you can't really draw any firm conclusions one way or the other. In this particular case though, Ranty Flat Earth went out earlier this week and made some observations of a lighthouse a little over 13 miles away, proving that 65 feet of that lighthouse are being obscured by the curvature of the earth. So for today, and today only, cancel all those warnings, put the oven mitts away. We're just going to have a look at some good solid evidence. Hey Gladys, go get those marshmallows. No, I didn't go to the store. You said you were going to the store. What? You telling me we're out of marshmallows again? Gladys, come on. Gladys. 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 This is the lighthouse Ranty was observing. This is the lighthouse at Walney on Walney Island. Let me see if I can show that to you on Google Earth. This is Walney Island right here, and the place mark is at the lighthouse. We can zoom in and have a look at it. There you see the lighthouse. Ranty was 13.25 miles away, so that puts him right about here somewhere. In fact, I think he was right about where these steps are. He takes quite a few observations from this general area, so it sort of makes sense. Let's listen to some of Ranty's commentary on his video.
Morning, and this is another video that I've done this morning. I went down and I was trying to observe Walney Lighthouse at night time whilst it was still dark. And what do you know? Of course, we see Walney Lighthouse from a distance of 13.25 miles away, and the height was just 2 feet. Now then, it's important to get some calculations done here, because in the globe model we have a sphere and we have water, being acted upon by the Earth's gravitational pull, which turns the globe into a globe. That's what it does. It makes water curve. Now, obviously we have a calculation for that. It's 7.98 inches per mile squared. Now, that is a calculation that has to work on water. It has to, in order to get the size of the Earth that we are told that we live on.
Okay, Ranty, let me stop you for a second. The old 8 inch per mile squared formula is an approximation surveyors have used for years. It gives surprisingly close results, but it is a measurement of the drop, not the amount of hidden. This is something that flat earthers frequently get confused. When we talk about drop is the distance from a tangent line at the observer to the base of an object being observed. As you can see in the bottom diagram, this is Walter Bisland's calculator we're looking at. The amount of drop is substantially greater than the amount of hidden distance. So it's easy to confuse yourself with this. Let's use your example. 13.25 miles squared times 7.98 inches per mile squared divided by 12 inches per foot gives a result of 116.75 feet. That's really pretty close to what the calculator comes up with of 117.078 feet. Only about 3 inches off, but it's the drop. It's not hidden. It's not visible. It is the drop distance. And that number by itself doesn't do us a lot of good now, does it?
No. let's put those details into a curve calculator. So looking across water, which is being acted upon by gravity, pulling it at 7.98 inches per mile squared around and around and around, what we get is we get a hidden geometric of 88 feet, and including refraction, which we all know is nonsense, 74 feet. Now then, what is the height of Walney Lighthouse? Well, Walney Lighthouse has a focal height of 70 feet according to the Lighthouses of Northwest England, and by Wikipedia 69 feet. Now that's 69 feet above mean sea level, so that is the central point over the entire year of what the height would be. So for instance, if you had a tide height of 4 meters at low tide and 6 meters at high tide, the mean sea level would be in the middle point of that, so 5 meters. Now in this location where I live, we have a tidal change generally between 1 meter and 8 meters. Occasionally you get it up to 9 meters, and occasionally it goes down to 0.3 or 0.2 even. But in general it's between 1 meter and 8 meters. So that would put the mean sea level around about 4.5 meters for this location. So that's interesting to note, because today when I went down to do the filming, what we have, this is Thursday the 5th of December, and if we go to essentially 7 o'clock, 6:56, it's the nearest I can actually get to the time that I was filming, we get 5.89 meters, so that was the height of the tide. Now that is higher than mean sea level, which means that we have to account for that by subtracting the additional height of the tide at that time from the focal height of Walney Lighthouse, to be accurate. So we're looking at 1.3 meters or thereabouts, let's say 4 feet. So we're going to take 4 feet off the focal height of Walney Lighthouse. So we're looking roughly between 65 and 66 feet above actual sea level was the height of Walney Lighthouse when I was filming it this morning.
The distance from Ranty to the lighthouse is 13.25 miles. The focal height of that lighthouse is 69 feet above mean sea level, but on that particular day the tide height was 4 feet. So the effective focal height is actually 65 feet. Got it.
One other thing I would like to talk about today was the very strong winds that you'll see in the, well, you won't see the winds, but you'll probably hear the winds in the video, and you'll certainly see the chop and the how high these waves were today. Now this is for today. This is the forecast. Obviously, we're looking 2 to 3 feet strong chop. That's wind-driven waves, and we also have a swell. So swell is completely different. That's something that's storms that happen a long way away, hundreds if not thousands of miles away, causes a swell eventually to arrive in this location, in all locations throughout the world really. Everywhere has swell for the most part. In this particular case today we're looking at swell of between, well, swell 3.5 feet every 5 seconds, and we're looking at 2 to 3 feet of wind-driven waves on top of the primary swell. So if you look at this graph over here and you see this is the let's say this is the swell. So that is the primary swell, 3.5 feet, and above that you'd have the wind-driven waves too. So we're looking at 3.5 feet or 2 to 3 feet. So all this is blockage. Now I'm trying to film from 2 feet. I'm trying to film from 2 feet. So essentially I am lower than the peaks of these waves. That's also something interesting to take into account.
That's a really good point, Ranty. On this particular day, you had a combined swell plus wave height of about 6.5 feet. Now, you subtracted 4 feet from the focal height of the lighthouse, because of the tide. But now when we consider the trough of a wave and swell occurring right at the horizon line along our line of sight, the focal height of the lighthouse is actually about 68.25 feet.
Now, without further ado, I shall show you the footage that I captured this morning. And, well, before we go there, if we see Walney Lighthouse, that means that it doesn't conform to the 7.98 inches per mile squared. It doesn't conform to that.
Hold on there, Professor. We're not trying to figure out the drop height here. We're trying to figure out the hidden height. 7.98 inches per mile squared is drop. That is nowhere close to what the hidden number actually is. We've still got some ciphering to do, buddy.
What does that mean? Does that mean that we don't live on a globe? No. It means that what we are viewing in the globe model is a hologram. In fact, everything that you see below 7.98 inches per mile squared on a calculation, if you ever see that over water, ever, it is always a hologram. It isn't really there.
Help me, Obi-Wan Kenobi. You're my only hope.
Think about that. It doesn't matter if it's just a few feet of something that you see. Right, let's see. Well, we saw the lighthouse there. If I get right down, so I'm approximately 4 feet above actual sea level here, so let's go down as low as I can.
The lighthouse is clearly visible from an observer height of 4 feet.
So we're going to go down to 1 foot.
Ranty caught one brief flash visible from a height of 1 foot, but that's the only one that was seen. Essentially, 1 foot elevation is not sufficient to see the lighthouse.
So there we saw it there, so maybe if I go to 2 feet instead of 1, we might be able to get over those breakers. Would help if I pointed it in the right direction, I suppose. There we go. Hey, we saw it.
And I agree, from a 2 foot observer height, the lighthouse is visible occasionally, not all the time, but you can catch it from time to time. Let's do a little data analysis. I've got Walter Bisland's curve calculator here. I've selected standard atmospheric refraction with a K value of 0.17. We'll start with an observer height of 1 foot, a target distance of 13.25 miles, and a target size or height as we figured out earlier, of 68.25 feet. At a 1 foot observer height, 78 feet are hidden. Obviously, the 68 foot target would not be seen. Let's go to 2 feet. At 2 feet, 71 feet of the target would be hidden. And of course the target is 68 feet, so it would still be hidden at a 2 foot observer height. But with variability in the wave action, that probably explains why we could only occasionally see the target at 2 feet. At 3 feet, however, hidden height is only 66 feet, so the target should be visible at that point. And at 4 feet, which is about where Ranty started, the hidden height is only 61 feet. Ranty saw exactly what he should have seen from a distance of 13.25 miles on a spherical Earth of the radius we say it is. The lighthouse is clearly visible from an observer height of 4 feet. You don't see the lighthouse at 1 foot, and you see it occasionally at 2 feet, depending on the wave action. So I think that pretty well sums it up. I want to thank Ranty for making those observations. That's quite helpful. I want to thank you guys for watching. Hope everybody enjoyed it. If you did, don't forget to hit the like and subscribe buttons. There's a link to the Patreon. You'll find it also up in the comments section. And we'll catch you guys on the next one. Hey, Gladys. We're out of here.